Okay, students, in this video we're going to be talking about normally distributed data. And if data is normally distributed, then there are certain calculations that are always true based on the data. If you have a normal distribution of data, then you know that 68% of the data lies within one standard deviation of the mean. You know that 95% of data lies within two standard deviations of the mean, and you know that 99.7% of the data fall within three standard deviations of the mean. So basically, if data is normally distributed, and certain data sets are, for example, the heights of adult men. In America, the average adult male is about 5'10". And we know this because of data, science, doctor's appointments where people's heights are measured. And we can calculate that the standard deviation for the data is about 3 inches. So we know that since the average height is 5'10" and the standard deviation is 3 inches, we know that 68% of men are plus or minus 3 inches away from 5'10". So we know that 68% of men are in between 5'7" and 6'1". 95% of the data is within two standard deviations. So two standard deviations would be 6 inches. So we know that 95% of men are in between 5'4" and 6'4". And we know that 99.7% of data lies within three standard deviations. Well, three standard deviations would be 9. So 99.7% of men are in between 5'1" and 6'7". So that's how we do some calculations if we know that data is normally distributed. Let's look at now some examples from the second trimester exam. Number 2, a study shows that 82% of the selling prices of houses in an area are within one standard deviation of the mean. Is this a normal distribution? Well, the answer is going to be a quick no, because we know that if data is normally distributed, only 68% of data is within one standard deviation. So here we know that this is not an example of a normal distribution. Problem number 3, sketch a normal curve that has a mean of 36 and a standard deviation of 2.5. Well, what we're going to do is we're going to go to a number line, and we'll set up our mean in the center, which in this case is 36. And a normal curve kind of looks like a bell. That's why they call it a bell-shaped curve. And you know that 68% of the data is within one standard deviation of the mean. And they tell you the standard deviation is 2.5. So we're going to go 36 plus 2.5, and we're going to go 36 minus 2.5. And that's going to give us a range of 33.5 and 38.5. So I'm going to label those 33.5 and 38.5. And that tells me that 68% of the data is going to fall between those two values. Since you know that 95% of data lies within two standard deviations of the mean, well, 2 times our standard deviation, 2 times 2.5 is 5. So we're going to take 36 and we're going to add 5. And we're going to take 36 and we're going to subtract 5. And that tells you that 95% of the data is going to lie between 31 and 41. And then since you know that 99.7% of the data lie within three standard deviations, 3 times our standard deviation, 3 times 2.5 is 7.5. So we'll take our mean 36 and we'll add 7.5 to it. and then we'll take 36 and subtract 7.5 from it, and that's going to give us the range within 3 standard deviations. So here we know that 99.7% of the data is going to lie between 28.5 and 43.5. That's going to represent 99.7% of the data. So if you can recognize a data set as being normally distributed, these percentages we know is true based on the data. People's heights, people's weights. These are examples of normally distributed data. Problem number 7, the scores of a recent test taken by 1,500 students had an approximately normal distribution with a mean score of 240. So what I'm going to do is I'll draw my normal distribution curve, and the mean goes in the center, 240, and it has a standard deviation on this test of 32. So basically, if I take the mean and I add and subtract 1 standard deviation, that tells me that 68% of the scores on this test are between 240 minus 32 and 240 plus 32. So that tells me that 68% of the scores on this test are between 208 and 272. So I'll label those on my normal distribution curve. Since I know that 95% of the data lies within 2 standard deviations, if I take the standard deviation of 32 and multiply it by 2, that gives me 64. I know that 95% of the scores are in between the average 240 minus 64 and the average 240 plus 64. So I know that 95% of the scores on this test are in between 176 and 304. And that's going to be important because if you notice what the question says determine the number of students who scored between a 176 and a 304. Well, since that range is 2 standard deviations from the mean, I know that 95% of the scores are going to be between 176 and 304. So 95% of the scores. But since they told you that 1,500 students took the test, we know that 95% of 1,500 have to score between 176 and 304. So that tells me that 1,425 students had to score between 176 and 304. Now, there's another way of doing this kind of a problem directly on your graphing calculator. What you do is you go to the distribution feature of the calculator, which is second and variables for the distribution feature, and you go to number 2, which represents the normal distribution. Now when you go to this number 2 allows you to type in the mean, which is the Greek symbol mu, of 240. The standard deviation sigma is 32. And then the range we want to know about is in between 176 and 304. So we type in the lower is 176, the upper is 304, go to, then paste, and what it'll do is it'll paste it on the main screen of the calculator. Then press enter again, and it gives you the approximate percentage of the scores that, if you have a normal distribution, lie between 176 and 304. It tells you about 95% of the students. So 95% of the 1,500 is 1,425. So if you can recognize a data set as being normally distributed, you can go to the distribution feature of the calculator, which is above the VARs button. A test given to 600 students was normally distributed and graded out of 100%. The mean was 86.5, so we'll go over to a number line, and it says the mean is 86.5, and the standard deviation was 3.75. Draw a normal distribution curve, including the x-axis, so that's what this this horizontal line represents, representing 3 standard deviations from the mean in intervals of 5%. Okay, so basically they want us to use intervals of 5%. We know that this test goes up to 100, so we'll label every 5. And now we'll put the key values into our problem as far as the mean of this test, which they tell you was 86.5. So we'll make the mean 86.5 and the standard deviation to be 3.75. So since we know that 68% of the data lies within 1 standard deviation of the mean, we'll take the mean, we'll take the 86.5 and subtract 3.75 and add 3.75. So that's going to tell us that between 82.75 and 90.25 in this region, we know that 68% of the students scored between those two grades. Since we know 95% of the data lies within 2 standard deviations, I'll multiply 3.75 by 2. So 2 standard deviations is 7.5. So I'll take my mean, which is 86.5, and I'll subtract 7.5, and I'll add 7.5. So that tells me that 95% of the data lies between 79 and 94. So in this range, between 79 and 94, I know that 95% of the data lies in that range. Here they want us to go to 3 standard deviations. So 3 times the standard deviation, 3 times 3.75 is 11.25. So I'll add and subtract 11.25 from our mean. And that's going to tell me that 99.7% of the data lies between 75.25 and 97.25. So 99.7 of the data lies between those two values. The heights of a certain group of adult birds was found to be normally distributed. The mean height is 38 centimeters. The standard deviation is 6.2 centimeters. In a group of 200 birds, how many of them would be more than 28.7 centimeters tall? So here's basically what we have going on. I know we have this normally distributed height of birds. I know the mean height is 38 centimeters. They tell you the standard deviation is 6.2. I want to know how many of these 200 birds are more than 28.7. Now, since the mean is 38, I know that 28.7 is going to be somewhere over here. And basically what I want to do is I want to try to figure out what percent of the birds, of these birds are going to be bigger than 28.7. I want to try to figure out what percent. So what I'm going to do is this. I'm going to use that distribution feature of the calculator. I'm going to go to second and then vars for distribution and go to option 2 for a normal distribution. They tell you the mean height is 38, so mu is 38. The standard deviation is 6.2. And I want to try to figure out the percentage of the birds whose heights are bigger than 28.7. So I set my lower limit to be 28.7. And now my question is, what should I set the upper limit to? I just want to find the heights of the birds that are bigger than 28.7. Now maybe if the average bird is 38 centimeters, maybe there's going to be a bird that's 50, 60, 70 centimeters tall. I have no idea how big the tallest bird is, but what you can do is this. It's really not going to make that big of a difference how big of an upper bound you give it, because basically any bird that's really, if the average is 38, who's like 60, 70 centimeters tall, it's such a small percentage that it really won't change your value. So what I always tell students to do when you need an upper limit is just to make it all 9s. It's not really going to throw off the percentage that much. About 93% of these birds are between 28.7 and whatever that huge number is. So 93% of the birds, they tell you there's 200 of the birds, so do 93% of 200. Here we have 186 of those birds. Now, problem 9 is a little bit different. Determine the standard deviation of the data that has a mean of 127.5 with 68% of the data ranging from 121 to 134. So here's what we got going on. We have our normal distribution. We have our mean of 127.5. And they're telling you 68% of the data is between 121 and 134. Now, you know that in a normal distribution, 68% of the data is within one standard deviation of the mean. So I know that within one standard deviation, so basically, if I go one standard deviation to the right, and if I go one standard deviation to the left, I have to fall between 121 and 134. So what I'll do is I'll call the standard deviation x. If I go one standard deviation to the right, that's x. If I go one standard deviation to the left, that's also x. I know that x plus x has to be this difference. Between 134 and 121 is 13. So I know that 2x has to equal 13, so x is going to be 6.5. So I know my standard deviation is going to be 6.5 for this set of data. A class math test has a mean of 83 and a standard deviation of 6.33. If a student is told they scored in the 50th percentile, what is his score? Well, here's what's going on. When you have this normal distribution, you're basically taking large sets of data and making assumptions based on these percentages. And in the normal distribution, it's assumed that the mean, the median, and the mode will all be about the same value. So basically what's happening is this. If you take the math SAT scores from everyone who took the May math SATs, there could be hundreds of thousands or even millions of kids who took the SATs. And whatever the average score is, the median score would be so close to it, and the mode score would be so close to it that we just assume for the normal distribution, the mean, the median, and the mode will be about the same thing. So the 50th percentile, that in statistics is the same as the median, because basically we're looking for the value that 50% of the people scored better than, and that means 50% of the people scored less than. So the 50th percentile is the median, but since in a normal distribution the median, the mean, and the mode are all about the same, we're going to say the median is also going to be about 83. So that's just the definition of the normal distribution. It's used for large sets of data to make percentages based on these established numbers. The weights of 60 students were recorded. If the 25th percentile of their weights was 160 pounds, what is the total number of students who weighed more than 160 pounds? Well, this kind of ties into a box and whisker plot. As you know, on a box and whisker plot, you have 5 values: the minimum, the lower quartile, the median, the upper quartile, and the max. And the significance about a box and whisker plot is that 25% of the data is between the minimum and the lower quartile, 25% of the data is between the lower quartile and the median, 25% between the median and the upper quartile, and 25% between the upper quartile and the max. So since they're telling you the 25th percentile, another name for the 25th percentile is the lower quartile, because 25% of the data is beneath you. That means 75% of the data is above you. And this particular question is saying, what is the total number of students who weighed more than 160 pounds, more than this 25th quartile? So basically, we know that 75% of the data is greater than this lower quartile. It's greater than this 25th percentile. So 75% of the 60 students weigh more than 160 pounds. 0.75 times 60 means 45 students weigh more than that 160 pounds. Problem number 6, name the 3 measures of dispersion and the 3 measures of central tendency. While in statistics, the 3 measures of dispersion are the variance, the standard deviation, and the interquartile range. The measures of dispersion measure how spread out the numbers are. The 3 measures of central tendency in statistics are the mean, the median, and the mode, and they all give the approximate center of the data. That's why when you have a normally distributed set of data, we just assume that the mean, the median, and the mode are about the same value because they're all at the approximate center of the data. Finally, number 10, the average score for a Latin test is 77 and a standard deviation of 8. Which percent best represents the probability that any student scored between a 61 and a 93? Well, we can do this question in one of 2 ways. Here they tell you the average score is 77 and the standard deviation is 8. So I could add and subtract 8 from the mean to get between 69 and 85. So that's the range that's within 1 standard deviation of the mean. That's the range that contains 68% of the data. I could then add and subtract another standard deviation. I could add and subtract another 8. That would put me between 61 and 90. 3. That's the range that contains 2 standard deviations from the mean. So since you know that within 2 standard deviations of the mean, 95% of the data must fall, one way to get this answer of 95% is to draw out your chart. But what would have happened if these numbers wouldn't have been nice numbers? What would have happened if it would have said between 63 and 92 or 66 and 95? Remember, you could always use that distribution feature of the calculator. I could go to second and then vars for distribution. Go to option number 2 for the normal distribution. And I could enter in my information for the problem. I want to know the percentage of scores that are between 61 and 93, if the mean for the test is 77, and the standard deviation for the test is 8. And here the calculator tells me that about 95% of the data falls in that range.